Hey everybody, Mr. Plantt here, and today we are going to be going over angular momentum. Um, Angular momentum is pretty similar to linear momentum. There's just a couple of kind of key different variables that we'll be using when we calculate angular momentum. So first, let's talk about what momentum looked like in the linear world. So when we looked at momentum in the linear world, we really talked about two main things, right? We talked about what is momentum. And then also we had this other thing called impulse. So real quick, right? Momentum was really just this measure of an object's mass multiplied by its velocity. It's kind of like a measure of an object's movement. And it's kind of a hard thing to really define clearly. But we had an equation for it, which was just our momentum, which was this letter P. And it was just the mass of our object multiplied by the velocity of the object. And we measured it in these units of kilograms meters per second. Okay, and with momentum, we had this thing called the conservation of momentum, which just told us that our momentum before has to equal our momentum after. But the one thing we can do to change our momentum is this thing called impulse, right? Where impulse was really just, we even said, just delta P, right? A change in momentum. And we could calculate it by taking the force on our object and multiplying it by how long that force was acting on our object. Okay, now this is real quick review of the linear stuff just to kind of help us see the tie-in when we start talking about it in the rotational world. So there's definitely more information here that I'm leaving out, um, but just real quick review of this momentum and impulse stuff. So now if we want to talk about things in the rotational world, we need to change the units we are using when we talk about angular momentum and then this angular impulse, right, in the rotational world. So in rotational land, um, let's write out some definitions real quick. Right, we have angular momentum. And all angular momentum really is for us, similar to how normal momentum was for linear, angular momentum is just a measure, let's see, a measure of how much rotational motion, so how much an object rotates, and so how much rotational motion and rotational inertia an object has. So let me finish writing this. Rotational inertia an object has. Awesome, that's angular momentum. And so with linear momentum, it was mass times velocity, right? Well, when we talk about things moving in circles, inertia isn't directly just mass anymore. When things are moving in straight lines, our mass and our inertia are, I always said like stepbrothers to each other. They're very, very similar and they're kind of directly related. But in the rotational world, that mass becomes inertia, right? This rotational inertia that we've been talking about. And the velocity kind of characteristically becomes our angular velocity. So our equation for this looks like so. L equals I omega, where we have some units for these things that we need to talk about. So first and foremost, L is just our angular momentum. That's our letter for momentum. For in the angular world, I don't, they always have weird letters for momentum, so kind of a fun little game to play. I, in this case, is our moment of inertia, or that rotational inertia, this moment of inertia, and it depends on the type of object and how it's rotating, as we learned. And the type of object you have, what axis it rotates about, dictates what type of moment of inertia it has. And then we have this omega, kind of just looks like a W, especially when I write it, but it's angular velocity. And each of these things has units, which is important because we want to understand what the units for our angular momentum are, because they are different from linear momentum. They aren't the same units. In fact, angular momentum units are measured in kilograms meters squared per second, which is a little bizarre. So let's see if we can figure out where that comes from. Well, moment of inertia is mass times velocity squared, not mass times velocity squared, mass times radius squared. So that's kilograms meters squared. Okay, and then angular velocity is radians per second. So if we combine these things together, we get kilograms meters squared per second, because remember, radian isn't really a unit. It's kind of a placeholder that we just use to describe some circular motion. So if we break this down a little bit, this kilogram meters squared per second, if we pull out one of the meters, you get kilograms meters per second. So our normal momentum times another meter, right? And this other meter is actually our radius, right? From the moment of inertia, that radius we had built in, and this m is just our radius. So really, very similar to how everything has been in circular motion, our angular momentum is kind of just the units for our normal momentum multiplied by the radius of rotation that it's going around. Okay, so it's kind of that theme of we're just multiplying a radius into everything. Okay, so that's angular momentum. We also have angular impulse. Okay, so angular impulse is very similar to linear impulse, except for, you guessed it right, we have some new units. So angular impulse. A definition for angular impulse is just a change in angular momentum. Just like normal impulse was a change in normal momentum, angular impulse is a change in angular momentum. And because it's just a change in angular momentum, its units are going to be the same as angular momentum. Let's look at that through the approach of an equation, right? So our angular impulse, we would just call this our delta L, and that is equal to tau times time. So T times T, a little bit weird because we're using Greek letter T's and non-Greek letter T's. Okay. Here, let's break these down into kind of what each one is, right? Uh, this is our change in angular momentum, right? L is our change in angular momentum. Tau is our torque. So that's our angular force. And then T is kind of the uniter of all things, right? It's just time that the torque is acting. So one way I like to think of it is if I'm screwing in a nail into a board, the time is how long I'm applying that torque to get that screw to go into the board, right? So time that the torque acts. And the units for all these things aren't too crazy. The change in angular momentum, we could think of it as a torque times a time. So it could be something kind of like a Newton times a meter times a second, which is a little bit of a goofy way to think of it. But a Newton is a kilogram meter per second squared, right? Kilogram meter per second squared times a meter times a second. So some of these cancel out, and we're left with this big unit of You get the same thing as angular momentum, right? That we get kilograms meters squared per second. That is our unit for there. Torque was still a Newton times a meter, a Newton meter, right? The force times the radius. And then time is just always measured in seconds. Easy peasy lemon squeezy. And so that's pretty much it. Even our problems when we solve things with angular momentum are very, very similar to linear momentum. We have just new variables we really use to solve them. Instead of forces and masses and velocities, now we're using torques and moments of inertia and angular velocities. And we can even substitute things in, right? Like omega, we can substitute in its linear velocity equivalent with our v's and r's, and then we can start combining things together. That's what I think is probably the most challenging part with circular motion is the concepts are all really the same, but now we have so much information that we can kind of be substituting in for each other. We have to get really comfortable with knowing how we can turn one piece of information into another. So last couple things. So one big thing to watch out for, we'll do this in orange, right? One big pretty common misconception is the idea that any external force acting on a system can create a change in angular motion, right? So any external force acting on a system will change angular momentum. Let's hope I'm spelling all these things right as I'm scribbling through this real quick for you guys. This is wrong, right? This idea is wrong, right? There's a big key thing here as to why it is wrong, and it has to do with this word right here, force. Okay, not every force acting on a system will change the angular momentum. Right? The better way to say this, the more correct way, is that um, only a net external, so it has to be external to our system. It can't be coming from within our system. So only a net external torque is gonna change our angular momentum. That is really important. It's a big idea that not all forces are torques. Okay, so only a net external torque will change angular momentum. Big, big idea. So just something to keep in mind. Okay, so the last thing we need to talk about then, we've talked about, if we look up here, right, angular momentum. We've talked about the units for it. Now we have an equation where we can start solving problems with angular momentum. We talked about angular impulse. So how does that angular momentum change and how do we describe that with an angular impulse? Um, we talked about some kind of big misconceptions with forces versus torques. Now we need to talk about the conservation of angular momentum. And this is a big idea. And there's some cool stuff that we can watch to see how it works. So conservation of angular momentum. Right? And we can think of it, right, as that our angular momentum before something happens has to be equal to our angular momentum after something happens, unless we are acting on our system with a net external torque. I actually like to word it a slightly different way, and that is when an object changes shape. And so when we say changes shape, what we're really getting at is that we're changing its rotational inertia, right? We're changing its moment of inertia by changing its shape. Right? So when an object changes shape, its angular velocity must also change. Will also change. As long as, right, if there is no total or no external torque. No external torque. Okay, and so this is going to make sure that our total angular momentum remains constant. The only thing that's going to change our total angular momentum would be a torque. Now, we have lots of cool ways we can think about angular momentum in places we've seen it. If you've ever gone to some of the playgrounds where they have these spinning discs you can stand on, and you can spin them around and like you'll push your body away from it. Let me draw a picture, right? So you have these little discs on the ground, and they generally have some sort of pole you can hold on to in the middle. And they'll spin around and around this direction or the other direction. And let's say you are holding on like this, right? Your mass is kind of kicked to the outside. If you were to pull your body inwards, your angular momentum would stay the same, but your angular velocity would not. Because as you pull yourself in closer, you are changing your rotational inertia, right? More of your mass is located closer to the axes of rotation, the pole that you're holding on to. What this means is that it requires less force or less energy to get you to spin around. So um, if your rotational inertia is changing shape, then your angular velocity also has to change. In this case, because you're getting closer, right, you're bringing that mass in closer, it's making it easier to spin faster, you will spin faster. I'll have two little circles to show. Faster. Now we can see this in a lot of different places. I skateboarded growing up. So if you guys know who Rodney Mullen is, he was this big freestyle skateboarder who did a lot of spinning on the ground with his skateboard, and you could see it all the time. He would pull his arms in to spin faster. The classic example is an ice skater. So let's actually do this. Okay, let's watch this quick video on this ice skater, if it will load. So it says the physics behind skating. So we see a couple different types of spins from this ice skater. Notice here how her legs kicked out, her head's kicked out sideways, slower spin. Then she gets down and brings her body in, spins a little faster. And then here, when she pulls those arms and legs in, that rotational velocity really picks up. Let's watch that one more time. All right, so this first one, her mass is spread out pretty far away from her axis of rotation, which is her left leg. And then here, she pulls it in a little bit, so still spread out a little bit. And then in this final upright spin, she really tucks in her arms and legs and gets spinning really, really fast. That is the whole idea of conservation of angular momentum, right? Just the idea, let's see if I can get back to where I need to be. Just the idea that when we change our shape, when we change our rotational inertia, our angular velocity also has to change. All right, guys, that is pretty much the basics of angular momentum. A lot of this circular motion stuff is kind of simple on paper, that we see it as just, a similar equation with different variables, but it takes a lot of practice and a lot of dedication to really start wrapping your brain around how all of this works. Okay, so stay patient with it. Make sure you're getting your practice in, and definitely make sure to bring any questions you guys have to our to class with us. All right, take it easy, guys. Bye bye.